This video is going to focus on combustion analysis. What you see happening in this picture is a compound, typically a hydrocarbon, which contains just carbon and hydrogen, but it could also contain other elements like oxygen, sulfur, nitrogen. It is heated in the presence of oxygen, and as it goes through that process, it's put through a series of tubes, one of which will absorb the water, one of which can absorb the carbon dioxide and allows any unused oxygen typically is your excess reactant, to be released at the end. The water absorber and the carbon dioxide absorber can be used to determine masses of water and carbon dioxide generated by the combustion of this compound. And from that information, we can determine the amount of carbon and hydrogen that was present in the compound, and from that, the empirical formula. So typically a combustion reaction contains a compound with carbon and hydrogen, but again, it could have other elements. We know this is combustion because oxygen is a reactant, and this particular combustion reaction, carbon dioxide and steam would be produced. We can use the amounts of carbon dioxide and steam to determine how many grams of carbon and how many grams of hydrogen were originally present if we assume complete combustion occurred. We can figure out the grams of carbon by using the molar mass of CO2 and the mass of carbon present in the CO2 to give us just the mass of the carbon. So basically we're taking the mass percent and figuring out the percentage of carbon in the original amount of CO2. And then we can do the same thing for the water, but we have to account for the fact that there are two hydrogens in H2O. If there is another element present, such as oxygen or something else, we would have to know what the mass was of the original organic compound that we combusted. If we know that and we know the grams of carbon and hydrogen, we should be able to find the grams of the remaining element. And you'll see an example of that in the problems I'm going to work. Once we have those masses, we can convert them to moles. We can divide by the smallest number of moles to get our mole ratios. Hopefully this sounds a little familiar. This should be like empirical formula. Once we get the empirical formula, we don't get to round off the fractions. We have to make sure we multiply. If it's a half, by everything by 2. If it's a third, everything by 3. Or if it's a fourth, everything by 4. Once you have that empirical formula, you could use that information along with the mass of the true formula to find the actual formula, aka the molecular formula. So we're going to go through two examples. The first one is going to involve combusting a hydrocarbon, which just has the carbon and hydrogen. We're given the masses of both the carbon dioxide and the water that's produced, and we're asked to find the empirical formula. We're given then if the mass of the molecular compound, the hydrocarbon, is 56 grams per mole, what would be the molecular formula for this compound? So we have the grams of CO2. We can use that and the molar mass of CO2 as well as the molar mass of carbon to go from grams of CO2 to grams of carbon, and that gives us the amount of carbon that was present originally in that hydrocarbon. For all of these problems, we're going to assume that 100% of the hydrocarbon is combusted. That's not what happens in theory, or excuse me, in actuality, but again, we're looking at it from a theoretical perspective, so we'll make that assumption. We're also going to take the mass of water. We're going to convert from grams of water to grams of hydrogen, accounting for the fact that there are two hydrogens in H2O. So that's why we use the molar mass of 18.02 and 2.02. That gives us that there are 0.1242 grams of hydrogen. I neglected to talk about the significant figures. I usually, when I'm doing these problems, because I don't want to round off too early, I keep the same number of sig figs that were present in my original compounds. So 2.703 had 4, 1.108 had 4, and so I keep 4 in my answers. At this point I have the grams of carbon and hydrogen, so I can convert to moles using molar mass, which is the next step in empirical formula. So I divide the carbon mass by 12.01, the hydrogen mass by 1.01, and when I do that division, I get 0.06142 moles of carbon and 0.1230 moles of hydrogen. Again, I'm not so worried about the sig figs because I'm trying to find the chemical formula that's being represented by these amounts, and so I just keep again the same number of sig figs I had in the carbon and hydrogen originally. At this point I have moles of carbon to moles of hydrogen, so I take the one that has the smallest number of moles, which would be carbon, and I divide both of them by it. That gives me a ratio of 1 for the carbon and really close to 2 for the hydrogen. So my empirical formula would be CH2. The mass of that empirical formula would be 12 plus 2 hydrogens at 1.01, and that gives me 14.02, but I'm thinking now that I've typed that, it should actually be like 14.03. When you divide the mass of the molecular compound by that mass of the empirical formula mass, it's really not going to make too much of a difference at 1/100th, because it's still going to give you a ratio of roughly 4. And that tells me my molecular formula is 4 times that of my empirical formula, which would be C4H8. So the second example I'm going to give you includes a compound that has a third element, such as oxygen. You would do the exact same thing we did in the previous compound to find the carbon and the hydrogen masses present after the combustion has taken place. So we're going to take the 41.98 grams of CO2, and we're going to convert from grams of CO2 to grams of carbon, and that gives me 11.46 grams of carbon. I'm going to take the 6.45 grams of water. I'm going to go from the 18.02 grams of water to hydrogen by using 2.02 for the mass of the hydrogen atoms present in H2O, and that gives me that there are 0.723 grams of hydrogen present. I had a compound that weighed 19.81 grams to start with. If I add the carbon and hydrogen together, I do not get 19.81, and that's because there was also some oxygen present. So if I substitute in the mass of the compound that was given to me in the original problem, 19.81 grams, I substitute in the mass of the carbon and the mass of the hydrogen, I should be able to solve for X. And when I do that, I get that the oxygen mass was 7.63 grams. So at this point I have the mass of the carbon, the mass of the hydrogen, and the mass of the oxygen. I can use all of that information to find the empirical formula by converting my grams to moles, dividing by my smallest number of moles. So I'm going to take the carbon and convert it to moles using its molar mass, 12.01. I'm going to take the hydrogen, convert it to moles using its molar mass, 1.01. And then I'm going to take the oxygen and convert it to moles using its molar mass, and that should be 16.00. Sorry guys, things were a little crazy this week. Once I do the divisions for those, I get 0.9542 for the moles of carbon, 0.716 for the moles of hydrogen, and 0.477 for the moles of oxygen. The one that has the smallest number of moles is actually the oxygen, so I would divide all three by that. When I do that, I get a ratio of, relatively speaking, 2 for the carbon, 1.5 for the hydrogen, and 1 for the oxygen. So my empirical formula would be double each of those ratios, because I can't leave it as a half. So the carbon would be represented by a 4, the hydrogen by a 3, and the O by a 2. Again, sorry for the couple of typos, and this should help you solve the problems with combustion analysis. The biggest way I can tell you to remember that you need to do this extra step here with the conservation of mass is, again, I'm going to have to tell you that the compound contains other elements besides carbon and hydrogen, so just pay attention to that. Also, if I give you the mass of the compound and the carbon and hydrogen don't add up to that, that should be another kind of clue that you're going to need to do that conservation of mass step to find the missing mass of the third element.